questions. So I have decided to actually talk about two questions I was asked most frequently last evening, and these are listed here. So the first question was about spin echo. So a few people came to me and told me, isn't this spin echo real old stuff that kind of people done in 50s, and why is it kind of important? So there are kind of different figures of merit one can use. One could say, well, just type spin echo and search physical review letter, science and nature over past decade, and see whether these words occur. But it's really not a reason for that to be important. So what I'd like to basically illustrate now is that it's true that the spin echo is a very old concept, but the way how things develop in science, and I guess I speak here from a very limited perspective, so my own experience is kind of limited, but what I already have seen during my own scientific life is that often science kind of goes around a little bit in circles, right? But hopefully with every circle your understanding improves and you can kind of see new things and can get some new insights. And spin echo is an example of this kind. So basically this was a concept which was developed in 50s and 60s, and it was clear that it was very powerful, but then basically it moved from the realm of physics to the realm of chemistry, and eventually to the technology like NMR, and this is technology there, right? People are using these pulse sequences and stuff like that. But then actually it came back into physics in a way which is both kind of very intriguing, but also perhaps important and with potentially high impact. So it came back during this time when people started worrying about quantum coherence, about quantum information and stuff like that. Just to give you, oops, lecture. Just to give you a little bit of an example why this spin echo is important, I'd like to talk about this kind of new application of the spin qubits, which we have been developing over the past few years, and this is an application to nanoscale magnetic sensing. So basically the motivation for this work is to extend the NMR and MRI techniques to a small scale objects, all the way down to single molecule or perhaps to single nucleus. So as you know, MRI is a general purpose technique, so it's a basis for many applications. You can basically, for example, scan your brain and other kind of living systems. But one of the holy grails of this field is really push this technique all the way down to basically be able to do magnetic resonance imaging on like single molecules, for example. And the reason why people are interested is that this kind of technique, if you can obtain sufficient sensitivity, might allow one to basically reveal the structure of very complex biological molecules, and also might allow one to monitor some kind of elementary chemical and biomedical processes, perhaps even in real time. But the problem is that implementing this is actually very challenging. So realization of this technique requires detection of a fairly weak magnetic field with some very good resolution, with nanoscale resolution. So the idea that we started developing a couple of years ago is very simple if you come from the kind of AMO point of view. So if you take an object like a single atom, which has unpaired electron spin. So if you place this object in a magnetic field, what will happen is that the Zeeman sublevels of the atom will shift in frequency. And if you can monitor this shift in frequency, if you can measure it precisely, you can then get a very accurate reading of magnetic field. So referring to yesterday's lecture of Bill, one could say that a good magnetometer is like an atomic clock, but it's just a very bad atomic clock. right? It's an atomic clock where basically where precession frequency is determined by the perturbation from the external magnetic field. So this effect is actually being used to construct atomic magnetometers already for a couple of decades. And our idea was whether applying this technique is to ask whether applying this technique to this kind of atom-like systems would actually result in some new kind of benefits. And it turns out the answer is yes. So essentially, we could think about NV center electron spin as just one atom magnetometer, where if we can measure the precession of the rate of precession of the spin, we can gain an accurate reading of the magnetic field. But sort of the big advantage of this system over other systems is that it can perform a local field sense. So think about the following. So suppose that you want to sense a field which comes from localized magnetic dipole, like one electron or one nucleus spin. So this field will actually be quite strong if you come close to this dipole. But it will decay very rapidly, as 1 over r cubed, as you go away. So for example, a 10 nanometer separation. The magnetic field produced by single electron is few microtesla. This actually is a relatively big field in terms of state-of-the-art magnetometers. And single proton gives a field of few nanotesla. This is actually also a sizable field. But the trick is that you have to bring the sensor very close to the origin of this field. And the idea here is that basically if you start with the NV center, which is, you know, which is localized in some kind of nanostructure, like diamond nanocrystal, for example, you can, if you can bring it close to the source of the field, kind of distances of 10 to 20 nanometers, then perhaps you can use the electron spin to sense this kind of field. So that's a basic idea. And one of the challenges, so it is actually possible to do this technologically, to bring the spin that close to the object you want to try to sense. But the problem, as I discussed yesterday, is that this electron spin is also subject to the perturbations from, for example, diamond nucleus. Right? That's was the origin of this decay coherence with T2 star. And so that's how the spin echo comes in. So remember, yesterday I was showing you the plot of the spin echo for the NV center, where we have seen this kind of echo modulation. So basically, if you just choose your timing such that you sit on the top of one of these peaks, at this point the electron spin is largely decoupled from the carbon-13, from the kind of local environment of the NV center. So you could say, well, okay, hold on a second. The spin echo technique cannot really be used for sensing, right? Because spin echo essentially eliminates the sensitivity to the constant perturbation, right? That's what I was teaching you yesterday. Is there anyone who disagrees with that? Well, the answer is actually, it turns out you can use spin echo to sense magnetic fields, but you can only not use it to sense DC, constant magnetic fields. So it turns out that the most interesting, in most cases, you actually don't want to sense the constant fields, you want to sense time-varying fields. And at this point, spin echo can be used. For example, if you have the source of the field such that basically the phase which is picked up during the first period of echo evolution is opposite to the phase which is picked up in the second period of evolution, then you can sort of have the benefits of both walls by using spin echo. You can decouple it from local perturbations, but yet be sensitive to the external fields. In particular, you become very sensitive to certain frequencies of the external fields. And that's the experiment which we've done a couple of years ago. So, for example, you can sit on the top of this echo and apply AC magnetic field with the frequency commensurate with this kind of echo, period. And then what you observe is that basically the echo, depending on the amplitude of this field, will start changing. And basically you can use this kind of slope, the dependence of the fluorescence in this case on the magnetic field to, for example, estimate the sensitivity. So this spin echo and its derivatives, so you can actually think about not just applying, one pi pulse, but also multiple pi pulses. Turns out to be extremely powerful technique for sensing applications. So if you know at least roughly what the frequency of your perturbation is, then you can just tune. You just essentially, kind of chop your Ramsey sequence into small segments by applying pi pulses, and then that way you actually decouple your system from the low frequency perturbation, but you become very sensitive to this kind of perturbation, which sort of resonates with the spin echo sequence.
What if you don't know your frequency?
What's that?
What if you don't know the frequency of your perturbation?
Yeah, okay. Then you sort of have to scan this. So it's kind of a little bit like Lukin technique. So in practice, the way I'm not going to talk about it in great detail, but so in practice, what we do is when we sort of start now sensing things which we really don't know very much about, like for example in the living cell, we start to do these experiments in the living cell. And there, what we do, we first measure T1 of our spin, then measure T2, then start applying these pulse sequences and sort of these different techniques. They are like if you want, you can compare them with some kind of knife. You can have an axe where you can just chop the wood, or you can have a carving knife, right? So this is like going in the direction of a carving knife. So often your perturbations are so big that basically the entire spin signal disappears, right? Then you don't need this kind of fancy stuff. But so what this fancy stuff is really needed is if you really want to push a sensitivity. And this is kind of the plot. So basically I learned when I was a graduate student that comparing kind of different techniques and in this business of measurement of for example fields is a dangerous business. So it's like so continuing this analogy with axe and knife. So there was a very famous Italian physicist who once gave a talk about the atomic magnetometers, and he said that kind of these different magnetometers is like different knives. You cannot use the knife that was designed to cut bread to cut a parma prosciutto. So that's kind of but basically, the idea here is to show that there is now a wide variety of different sensors. But if you plot the sensitivity versus detection volume, then what it turns out is that there are actually really not very many kind of small scale sensors. And the small scale sensors are the ones which are really needed if you want to do this kind of localized sensing. And so these first experiments which we have done 3 years ago started kind of filling in this niche, and sort of with some kind of more advanced techniques, for example, with more pulse sequences and so on, we are really now moving into this domain of this kind of empty territory, or what's it, like Arizona desert. But I don't want to spend too much time on this, but I just want to kind of illustrate that some of these techniques, they might result in some real applications someday. So, for example, so this is some work that we're doing with my colleague at Harvard Community Hobby. So what is shown here is a kind of a scaling tip. So this thing is actually carved out of diamond. This little tiny finger is carved out of diamond, and there is this tiny little pillar. And actually, right at the apex of this pillar, there is the single and center feature. So I'll maybe talk, if I have time, I'll talk at the end of this lecture how we actually make this kind of diamond structures. But with this, we already are doing kind of some warm up, kind of proof of concept experiment. So for example, this is an image of a classical hard drive, and the way how this image is taken is basically the tip is approached it is approaching the hard drive, and then in order to create kind of AC field to improve the sensitivity, the tip motion is excited. So in that way, kind of a DC field of a hard drive is converted to AC, and then basically you do this Spinnaker sequence and just you measure fluorescence, and then at different points, there is a kind of contrast, fluorescence contrast is basically a measure of magnetic. So perhaps kind of another even more intriguing example, and we're just starting to do this work, but we're trying to do the experiments also inside the living objects. So this slide shows all what I know about biology. So, so basically, for example, inside the cell there are different compartments. They're called organelles for simplicity. And these different compartments are responsible for different functions. For example, some organelle, which is called phagosome, is responsible for killing bad stuff. And what we can do now, we can take basically small nanocrystals, small diamond nanocrystals with MD centers inside, and basically functionalize their surface, treat their surface in such a way that if we inject them in the cell, they go to one specific organelle. And then what we can do is basically by doing Spinnaker, by looking at the Spinnaker response of different MD centers, we can actually measure essentially magnetic noise inside these different organelles. And this really tells us about some functions of these different parts of the cell. For example, it tells us about concentration of radicals, local concentration of radicals, which is actually apparently a thing which is very difficult to measure. So, okay, the bottom line here is that Spinnaker is a useful concept even in 21st century. Yeah.
It might also be useful to point out that Spinnaker later gave birth to photon echo, and today a lot of atom interferometers, things that use the Bourdet-Hall configuration, are really echo type experiments. So it's even broader than that.
Yeah, absolutely. Yes. So I just wanted to give one example, but
if anybody's wondering whether it's a useful technique, it's everywhere now.
Exactly. So going back to I guess the moral here is that going back to basics never hurts. Go back, understand these things deeply, and this will help you one way or another. All right, which brings us to the next frequently asked question. So I did not realize when I made this kind of off-the-cuff remark that that the block sphere is one out of 4 things that you need to know about the physics. But I will be asked what are the other 3 things. And so here they are. So this will be a blackboard. All right, so 4 things you need to know after you leave the school.
There are some seats for more to the front if you have a hard time seeing from the back. Don't be shy.
The funny thing with all those lights, the board is still in shadow.
Okay, so let's see if we get this. Oh, then we.
Oh, that's perfect.
Well, that's using the projector to illuminate it is great. Just move it back right against the screen, and we'll be fine.
I can actually model. High technology.
No, actually, the projection was good.
Okay. All right. Let's give it a try.
So there are lots of seats here, if you cannot see.
All right. So 4 things that you need to know, otherwise you demand your money back from here. All right. The first thing we already talked about, both I and B, the block sphere. So I hope that with the lecture yesterday, it is clear that the block sphere is an extremely useful concept. So you don't want, when you sort of think about these pulses and so on, you don't always want to go back and write this kind of unitary evolution and commute these operators. This is good, but this is not efficient. So the block sphere gives you an intuition. You can use it. Right. The second thing was mentioned by Bill, breath states. So when you see, for example, kind of your senior colleagues, us discussing and talking to each other. So what you realize is that we seldom kind of talk in terms of, kind of complicated equations. What we do, we draw some little simple pictures and we kind of write some simple equations. And so these are these kind of concepts, like dress states, which provide us very useful insights, which allow you to predict the answer before you even do the calculation or do the experiment. So what are the dress states? So the dress states, in the simplest way, is the following. So if you have two state atoms, ground state and excited state, and if you, for example, consider a semi-classical interaction, just a classical field driving this two-level transition with radio frequency omega and with the detuning delta, then once you transform the Hamiltonian into a rotating frame, once you get rid of this kind of fast, for example, optical frequencies, so this Hamiltonian becomes time independent. And what you can do is basically you can diagonalize this 2 by 2 matrix, exactly what Bill said yesterday. So you can diagonalize the system here and find two eigenstates, frequently called plus and minus. And these two eigenstates will in general be a combination of ground and excited state of atoms with some coefficients, and those coefficients will be determined by Manometers. These coefficients will generally be determined by the ratio of this radio frequency of the detuning. So in particular, so you can also find the energies of the states. So these energies of the states also depend on this delta and omega. So, so in particular, there are two important limiting cases. So one limiting case is when the detuning is equal to 0. So in this case, plus and minus states are symmetric and anti-symmetric combination of the levels. So simply in this case, what happens is that there is no detuning, right? So this field just mixes these two levels, and so the states are symmetric and anti-symmetric combination. And the energies of the dress states is basically plus minus omega. So this is the origin of something which is sometimes called Rabi splitting of the dress states. So using the dress state picture for zero detuning helps you to understand Rabi oscillations. Why is that? Well, if you start in a well-defined state, say G state, and then turn on the field abruptly. In this basis, this corresponds to starting in the superposition of these two states. And these two states now split by omega, so there is this omega time dependence. So the phase difference acquired between two dress states translates in the original basis to the transitions up and down. That's the Rabi splitting of the dress states. The second, perhaps even more useful application of the dress states is the situation where the tuning is much larger than the Rabi frequency. So in this case, the leading order effect is a big mixing of the states. So in this case, for example, a plus state will be almost equivalent to the ground state, but we'll have a little bit of admixture of the excited state, and vice versa. To the leading order, in this case, the energies of the states will be shifted basically through the second order perturbation field. So you can find, for example, either by using the second order perturbation theory or just by from these expressions, what you can find is that For example, omegaclass will be equal to minus delta minus omega delta, and omega minus is just this. So this thing is a level shift, which is often referred as AC star shift. So that's a very, very important concept in the atomic physics. So even if you don't remember a dress state, you must know what AC star shift is. Okay, that's the second thing that you need to know. So the third thing involves the presence of dissipation. And this is a concept of optical pumping. Suppose you still have this two-level system and your field is driving this transition, but suppose now the excited state decays. So it can decay back to the ground state or it can decay in some other states, it doesn't matter. What will happen in this case is that if you apply electric field, the dynamics now will not be coherent any longer. So you will not have, this kind of, coherent stuff like, radio oscillations or AC star shift. Only you'll have something else. So what you'll have is that population will now start leaving this ground state. And this kind of irreversible departure induced by a combination of the optical field and the decay is what I'm calling optical pumping. So basically, the optical pumping is essentially will be characterized by a rate of atoms leaving state G. So how can one calculate it? So there are different ways of doing that. So the proper way of doing it, of course, would be like multiplying something like master equation, but we don't have to discuss that now. So what I will do is I will show how to calculate this rate now using essentially a perturbation field. So suppose that the radio frequency is smaller than either detuning or this excited state. So in this case, what I can do is I can treat this field here perturbatively. So from the second order perturbation theory, a conventional second order perturbation theory will tell us that basically you have to just take the square of the matrix element which couples G of P and divide it by the kind of energy, kind of effective energy difference between final state and excited state. So in our case, because we are sort of applying the time varying perturbation, the effective energy difference will be basically given by delta, but not quite, right? Remember now we have this decay. And in this kind of kindergarten quantum mechanics course, when now we had decay, we said, oh, it's like the state has a finite lifetime, let's just include as an imaginary energy. This is good enough for us for now. So what we can do now, we can calculate it as basically omega squared, this is our matrix element, divided by delta minus I gamma, right? So that's our energy difference between, that's our imaginary energy. And now look, so if there is nothing, there's no decay, what we get is precisely, we get this AC star shift, the stuff which we just got from the state first. But now we have an imaginary part. This imaginary part will result precisely in this kind of departure, kind of finite lifetime of the level G. So in this case, we can basically rewrite this as omega squared delta plus gamma. Like this. So from here, basically, we can immediately read off AC star shift, discussed it already. And B, we can see that we have this kind of imaginary energy shift, which basically corresponds to the finite lifetime of the population in this state G, which I can now calculate as this. This is the rate of optical excitation by the coherent field in the presence of the decay. This is the third most important thing in the atomic physics. If you eternalized log sphere, dress state concept, and this stuff, you can do a lot of cool things in your life. Any questions?
What's the fourth one?
Any questions about what I have said so far? So how many people see this for the first time ever in their life?
I wrote it down in my lecture, so that it wouldn't be the first time now.
The first time, except for Bill's lecture. Okay, read about this. If this is something that is new for you, this is very, very important. Do not be confused about this simplicity of this and kind of naiveness of this appearance. These are the concepts. I mean, this is, this is, for example, a basis. This stuff is a basis for the subdoppler laser cooling, and among other things.
If you want to mention Fermi's golden rule in this context?
Well, yeah, it's kind of a Fermi's golden rule. Yeah, this is, you can also get it from Fermi's golden rule. Yeah, of course. This, you can derive this thing from using. It's a Fermi's golden rule. Yeah.
What is the name of it again?
Huh?
What is the name of it again?
No, this, I mean, like, to derive, so this is a...
Just for the purpose of looking it up.
It's optical pumping. So you can, for example, if in doubt, look at my lecture notes, look at the chapter devoted to like two-level block equations, and this is in there.
Okay.
Right? And you can derive it by Fermi's golden rule, if you correctly. Yeah, sorry, it's kind of, well, it's late night yesterday. So, okay, so there is one more thing. Yeah. So there is one more thing that we need to know, and I hope I get to it in my lecture today, but I will just mention it now, just for the record. So the last thing...
Can you use the top half of the black box,
yes.
please?
So the last thing that we need to eternalize is a concept which I'll call the G concept. So what G is a radio frequency of a single photon. So up to now, everything that I've discussed essentially involved classical field interaction with the matter, with quantized matter. So this thing requires us to quantize electromagnetic field. And what this G is the following. Suppose that you have a box, like an optical cavity. You put one photon in there. So what's going to be the radio frequency associated with that? That's this thing G. And this is something that you should remember in your sleep. And I'm going to derive it for you in such a way that perhaps you will remember. But this will happen in half an hour.
And sometimes it's called the vacuum rapid frequency.
It is.
That's right.
Which makes everything a bit confused.
That's right. So
In fact, most of the time it's called the vacuum Rabi frequency,
But
and it shouldn't be.
it should not be. And for that reason, I'm not going to call it this way.
No, but I mean, if you read papers,
That's right. That's sometimes called also known. That's right. For the record.
Yes, it's a concept that's used for
So this is the most fundamental concept of KD. Exactly. All right. Okay, that's my second answer to the second most frequently asked questions. Are there any questions about that?
add a fifth one,
Yeah, which is,
spontaneous emission.
it's in there.
It's well not quite, because you have to have mode density in addition.
So okay, that's a golden rule. Okay, that's I agree.
But just to give you an example, when he said optical pumping, I wrote down and spontaneous emission.
That's
It's good, it's already there.
So this spontaneous emission is right here. This is essential for this optical pumping, because optical pumping emerges as a combination of basically atom being excited by laser light and spontaneously emitting the photon. All right. With these 5 things, if you can eternalize them, you can do a lot of good things. Believe me. Any questions? All right, so let me kind of now just go on and a little bit and complete the lecture 1, which I hope will illustrate some of these things based on one specific example. So I've yesterday talked about the nuclear spin environment, and I mentioned that this is a very slow environment. So for this reason, in principle, you can have a chance of actually affecting it with your single quantum system. For example, you can either perform a measurement or you perform some kind of simple manipulation like cooling of this environment. And I'd like to now describe how this is a very recent work. I would like to discuss how this is possible to do it by using some of this concept of atomic physics which we just described. So the tool which I'm going to use involves another kind of very important kind of concept in the atomic physics. This is called coherent population trapping. So what is coherent population trapping? This is an effect which occurs in this so-called lambda type atom. So if you have a freelevel atom where you have 2 metastable long-lived states which are connected to a single excited state with the 2 fields in this kind of configuration, which makes a kind of lambda-shaped system, this is called lambda. So usually, I mean, if the atom starts its life, say, in ground state, and you start, exciting it at resonance, it of course absorbs light. It absorbs light and produces some, fluorescence, right? And the closer you are to resonance, the stronger is this effect. With this lambda atoms, something very strange happens. So it actually turns out that if you take these 2 fields and just, put them both in exact resonance, then right at the point where all of the fields are resonant with the respective transitions, the absorption as well as fluorescence vanishes completely. So this effect was actually observed by, I think it was observed by the same fellow who talked about the Parma-Prosciutto, and it's I forgot the name. That's
Mazzini?
it's people in Pisa who observed.
Yeah.
Rimonda and Gazier, exactly. And so this is, they observed this effect as a kind of dark line in the experiment. So what they had, they basically had a cell with the sodium atoms, and they applied the magnetic field gradient across this cell, and they did this kind of 2-color excitation of the cell, and then what they saw is that the part of the cell where all fields were seemingly in resonance, where it's supposed to be the brightest, actually it went dark. They called it a dark line. It's a dark resonance. So I'm going to talk now on a blackboard a little bit about the physics of this dark resonance. So in brief, essentially the formation of this dark resonance can be best understood in a kind of dressed state picture, where you essentially create a coherent superposition of these 2 states, of these 2 lower states, which is decoupled from light. And the important thing for our purposes will be that if you apply some external perturbation, like magnetic field, for example, you can destroy this dark state. Then the atom becomes bright. So, but just before kind of I spend another 10 minutes of our valuable time talking about this dark resonance, let me just emphasize that this coherence population trapping is really a workhorse of table physics. So it was one of the kind of some of the early idea, I think intellectually very influential idea to do sub-equal laser cooling. So it's also used for sensing. It's actually now used in the world's kind of smallest atomic clocks, not the most precise, but the smallest atomic clocks, which I think now you can even buy. It's commercially available. And it's also, of course, the idea behind this kind of slow and stop light and quantum memory. So what we are trying to do now is we are trying to apply these ideas to solid state atom-like systems. But before we go into these details, let me just, take a few minutes to talk to you about the physics of dark resonance, and perhaps this will illustrate why these four things which I told you are important are really important. All right, so I'd like to talk about dark resonances. Just to establish the kind of notations, so let's consider a free level atom. So let me call one of these levels +1, another one -1. This will eventually, kind of an experiment I'm going to describe, this will correspond to the M sub S sublevels of the B center, but for now it's not important. And then I have some excited state. And let me consider the situation where I have two fields that we call omega plus and omega minus that are driving this free level atom. So what I'd like to do now is actually, I'd like to write down the Hamiltonian for the system. But in this case it's actually very simple and intuitive Hamiltonian. Right? So I just have two classical fields driving two transitions, inducing two dipole moments. So what's going to be the Hamiltonian? So the first term will correspond to essentially field omega plus driving a transition between the excited state and the state +1. Right? So that's kind of, we've never seen it before, so this is kind of a dipole type Hamiltonian. Basically a field just kind of drives, induces a transition between these two levels, mixes these two levels. So then we have another term which will drive a transition between -1 state and B, and the excited state, the same thing. And then in addition, I'd like to include some detuning term. And the way how I'll do it is that suppose now I I will, by changing the frequencies of the field or by applying external perturbation like magnetic field, I shift these levels in the opposite direction. So suppose that this one is shifted up and this one is, for example, shifted down. And so this will kind of introduce tuning or energy shift if you want, and this energy shift can be now written as this. So this is like a kind of sigma, this is like a magnetic field for a two-level system, right? This is, if you want, BZSZ type term. So, okay, so let's first set this detuning to 0. Right? That's this kind of most intriguing point where everything is in resonance. And there is, sorry, and of course, there should be this, should be Hermitian conjugate. So, and what I can do now with this Hamiltonian, I can rewrite this in a way which will help us a lot with our intuition. So specifically, what I can do is the following. So I can just put some parentheses here and take this E out of here. So I haven't done, so I haven't done anything, right? I just, rewrote it, just put in parentheses. So basically, and then what I would like to do is I like to observe that this term responds to some kind of superposition of the two states, plus and minus. So what I'd like to do now is I'd like to introduce a new state here, which I'm going to call B. So it will be, which has to be properly normalized. But I'm going to call this a bright state. Right? So this bright state, at this point is like a very formal, involves very formal transformations from the original basis. Right? I just take a superposition of two original basis states and introduce this new state. So this is the so-called bright state. Okay, up to now I haven't done anything. But with all of this observation, I can make yet another observation. So in particular, I observe that there exists a state, which I'm going to call dark state, which is basically a state orthogonal to the bright state, such that if I act with the Hamiltonian on this dark state, the result will be 0. So why is that? Well, first of all, if I basically introduce any kind of linear transformation of this basis of plus and 1, of plus and minus, so I started with two states, which were orthogonal, then I should also end up with the other two states which are orthogonal. And if I construct this dark state, in fact I can write this down explicitly, in such a way that this dark state is orthogonal to the bright state, so B is 0, then if I act with my Hamiltonian on this state D, I'm guaranteed that the state will be a 0 energy eigenvalue of this Hamiltonian. Why is that? Well, clearly this dark state has no overlap with E, right? And clearly this dark state has no overlap with B. So this wonderful theorem is proved. Right? So basically, okay, so this is mathematics. So what we see now is that there exists some state which the combination of these two lower metastable states, which is 0 energy eigenvalue of this Hamiltonian. So what's the physical picture? So I've told you that knowing their states is very important, and that it's often good to guess the answer before you do the calculation. So what's this? How can you guess this kind of answer? So basically, what we can do now, we can basically transform our original system into this new basis and just try to see how this excitation and transitions work out in this kind of basis of bright and dark. So there is one state which is bright, I've argued, which is now coupled, to the excited state. And this, this coupling rate, if you do this kind of math carefully, then this will be actually given by the square root of the sum of the squares of these two fields. And so the excited state now can decay. But then there is this one state where if the atom drops in there, it will never stay. Right? So that's the physics of the dark matter. So as a matter of fact, no matter in which state you start, after a few cycles of spontaneous emission, you end up here. And then the dynamics stop. The atom is not excited, there is no fluorescence. Does it make sense? That's the essence of this dark resonance phenomenon. Does it make sense? Any questions? Okay, so let me just make a couple of simple remarks about this result. And the first remark is, you can ask what happens if this delta is no longer zero. So if this delta is not zero, then what we'll have is we'll have some kind of mixing between the bright and dark state. So as a matter of fact, if this term now transformed into a dark and bright basis, in fact what will happen is that this term will look precisely as a kind of coupling term between dark and bright state. So in essence, what this detuning will do is will basically mix these bright and dark states together, kind of like a Rabi coupling mixes the two level system. So you can now ask a question, for the, let's say, given detuning and the given decay rate and given the Rabi frequency, what will be the fluorescence rate of the atom? Right? So how can one answer this question? There are two ways to answer it, many ways, but I can present you two ways to answer the question. One of them is to write down the master equation, density matrix equations, and there are like 3 levels now, so there are 9 equations, differential equations, that you have to solve. That doesn't seem like a task we can accomplish in the remaining time of this lecture. But at the same time, you can use these 4 things, or 5 things, most important things, to actually write down the answer in one line. So how can we do it? Well, let's think about it. So first of all, you have now the field which now drives this transition. So consequently, there is some finite lifetime to this level B. So what's this lifetime? It is before this. To be precise, it's rule number 3. So the rule number 3 tells us that the population from this level will escape with the rate which is given by the square of the Rabi frequency divided by k. Right? Now, what we're interested in is we're interested in the rate of escape from D. So what will be the rate of escape from D now?
Probability of transitioning to B times the decay rate.
Okay, I want an answer in terms of detuning, Rabi frequency, and gamma.
Or delta times gamma.
Remember the rule number 3. I'm not making jokes here. I tell you that's a rule.
There is a rule number 6 also, which is what Bill said during his lecture, his public lecture. Scientists don't guess.
Exactly.
You have to think.
Exactly. Just
And remember what I said was, nature answers the question. That's what an experimentalist does. Here we're talking about theory.
Here we're talking about back of the envelope estimates, to be precise.
Exactly.
So that's the kind of stuff you have to do before you send in your proposal. Right?
But back of envelope estimate is not the same as guess.
It's not the same as guess.
That's right.
Well, this we are talking about actually, I'm not sure. So I would call, okay, so let me just write down this, this result and explain it, and then I want to make a point here basically. So okay, what is the rate of escape from this state D can be now calculated in the following way. So this delta here is like a Rabi coupling, right? So what we can do, we can again use this kind of golden rule, second-order perturbation theory, to say that this rate will be proportional to the square of this delta divided by what? Divided by the decay of this state, divided by the stuff which we've derived, right? So basically, that's the result. So, see, instead of kind of doing this sophisticated algebra and all going through these things, we could essentially guess the result, right? That's how, so the best thing you can do when you start doing some theoretical calculation or when you start to experiment is to guess what will come. And sometimes you will be surprised, but this is good. But the good guess and surprise will be also pleasant. Right? So this is the kind of, this is why these rules which I have described are real and important. Okay, so this is how the population kind of starts leaking out of the dark state as you change the detuning. So this also basically shows that the width of resonance, of dark resonance, will be given by this kind of effective radio frequency divided by the gamma. Right? So it's the only kind of relevant frequency scale here. So note that if this radio frequency is weak, then this dark resonance can be extremely narrow. Right? So in other words, one could say that this dark resonance is a kind of quantum interference effect, where you have kind of different absorption paths which start in different states but terminate in the same state, and there is some kind of interference. And these detunings basically break this interference. The interference is fragile. So this narrow width of the dark resonance is one of the main reasons why this is useful. This is useful to produce, for example, slow group velocity. This is useful in laser cooling. In laser cooling, if you make this delta velocity dependent, you can cool the system. If velocity is zero, then atom will not move anywhere. If velocity is non-zero, then the atom will be excited and will exhibit a kind of a random walk until it is in this dark state. That's the idea.
So at zero detuning, there's no bumping into the dark state.
Now at zero detuning, the situation is the following. Zero detuning, it depends on which state you started.
Right.
If you already started in the dark state, there will be nothing. There will be the atom will not respond. Right? However, if you started in the wrong state, if you started, for example, in the right state, then you will be excited and you will either go back to this right state, in which case you will be re-excited, or you will fall to this dark state. And once you're in the dark state, dynamics stops. Does it make sense? So actually, it turns out that this is one out of two ways to prepare the dark state. The other way is by using adiabatic passage. But this is beyond the scope of the lecture. It's also very interesting. This is chapter 7 of the lecture. All right. Any other questions about dark states? Yep.
But your new basis, you have spandings and
So yeah, so basically that's it. So this is only part of the dynamics. The other part is the important part, is that the excited state should have some decay, right, due to spontaneous emission.
so basically we have at least 3 dissipation channel, like to -1 and +1 and the up to the others. So can you express your gamma in terms of gamma 1, gamma 2?
Yeah. So I mean, this gamma. So you are right. There could be, in practice, there could be 3 different decays. The atom can spontaneously decay here, spontaneously decay here. They are both alternation. It can also decay to the outside of the system. So the process which kind of brings you back into this dark state is the process in which the atom is recycled, in which it goes back. This part of the decay which takes the atom outside, of course, will not bring you to the dark state, but will bring you to some other state. Right? But even in this case, if you somehow started in dark state, you will remain in dark state. Okay? All right. So the goal for me is today to talk about is to finish up by talking about this single photon Rabi frequency. If I can do it, then everything else is. But let me just talk a little bit about how this concept of the dark state plays out now in this context of the solid state atom-like system. So basically, what I'd like to show you is some recent work where we are actually trying to use these dark states now to do optical pumping or cooling kind of nuclear environment using dark resonances, and also using it to do fast projective measurements of nuclear states. So the idea is the following. So we actually like to implement this dark resonance concept in B centers, and the way how we have done it about a year ago is by just picking a certain optical transition which can be basically driven by the linear polarized light, such that 2 components of the linear polarized light, sigma plus and sigma minus, basically create this kind of lambda system. So this is a spin state, right? This is SMS equals 0, -1 and +1. This is one of the excited states, and we tune the laser to the transition such that we can actually make this lambda system with just a single frequency laser. So in order to introduce this detuning, we then, for example, apply magnetic field to the system, and this causes a level splitting, introduces 2 photons. So now this experiment is done on just single individual receptors. We just focus light and look at its fluorescence, change, for example, magnetic field. So in this case, sort of the first things which we observed are the dark resonances. So indeed we have a little bit of fluorescence drop here, but by atomic physics that they will not terribly influence. But then we started looking a little bit more closely, and what we see is if we use the power of laser, we actually start resolving some kind of individual substructure. So what is that? So this substructure turns out to be due to the nuclear spins that interact with the center electronic spin. So in particular, so these 3 distinct peaks are associated with the nitrogen nuclear spin. So this is kind of an intrinsic nuclear spin which is associated with nitrogen atom, which forms a center. So indeed, these 3 transitions can be viewed as basically kind of 3 hyperfine sublevels moving into resonance with this kind of 2 photon transition, and then we see these 3 distinct peaks. So these 3 distinct peaks correspond to different nitrogen nuclear spins. So okay, so with this kind of resolved sublevels, we can think about the system as a kind of similar to some like decay regime. So I don't know if someone talked about it. Maybe June talked a little bit about this decay regime, but We can basically, once we can resolve the sideband, we can clearly address them individually and try to basically manipulate or cool, the nuclear spins and do stuff like that. So, okay, here is one very simple example. Just, for the schooling, I'll just present one very simple example how this works. So, and this is the following. So suppose now we start a situation where we have zero magnetic field. So in this case, this M sub I, the nucleus spin zero state, will be in two-photon resonance. So if the nucleus spin is in M sub I equals zero state and the electron spin is in a dark state, then the NV center will not be excited. But if the nuclear spin state is not right, is not correct, if M sub I is +1 or -1, then what will happen is that there is this two-photon detuning, right? And according to the discussion, non-zero two-photon detuning. According to the discussion we just had, the NV center will get excited. So the NV center will get excited. In the excited state, there is a strong hyperfine interaction, so the nuclear states are mixed together, and then followed by decay after a few cycles, you will actually end up in this dark state corresponding to this, proper nuclear spin state. So I mean that's the idea of essentially cooling or polarization through the optical pumping. Does it make sense? Okay, so this is how we test this experimentally. What we do is just, we basically first do this pumping at some value of magnetic field, say 0 magnetic field. And then afterwards, we just, scan the magnetic field and, check what the spectrum of this hyperfine sidebands, how does it look like. And what one sees here, for example, if one pumps at the central peak, then one can basically, reduce the sidebands, which corresponds in this case to the cooling, to the cooling of the nuclear spins. Now, if you okay, that's good, that somehow mechanism works, but then you can also ask the question, well, somehow this is still not a terribly impressive dark resonance. I told you that it should go all the way to 0, but it does not, and it's actually also not particularly narrow, so it's about a megahertz broad, but of course megahertz is what corresponds to our T2 star. So let's try to understand what the causes the width of this resonance, and we talked about it yesterday, so we just talked about it. So we zoom on one of these peaks, and we have kind of an additional hyperfine structure. This hyperfine structure emerges due to this, carbon-13 nuclei, which are, separated, spread out all over the lattice. So the closer one will cause, larger hyperfine splitting, then there will be another one, and then etc. So because these carbon-13s are initially in a random state, we can be in any of these states, right? And this is a cause for broken. So this field, which is produced by nuclei, is sometimes called Overhauser field. So basically, in this case, what we have is a kind of quasi-continuous random value of Overhauser field. But remember, this Overhauser field has a long lifetime. So for this reason, what we can try to do is we can try to measure it rapidly. If we can measure it within its correlation time, we can actually basically eliminate this as a source of dephasing. So the way how we measure it is once again using the dark resonance. So in particular, note that if we can make this kind of scan of the magnetic field rapidly, we can determine the point where the fluorescence vanishes. This will tell us about the instantaneous value of the surrounding magnetic field. In particular, it will tell us about the instantaneous value of this nuclear field. So in essence, what we have here is basically we have a magnetometer. In this case, it's basically nearly single shot with the ring. Okay, so here is how these experiments work. So basically, we zoom on one of these peaks and start scanning magnetic field. And if we just average over many scans, then we get this kind of megahertz broad resonance. But if instead we don't do this average, if instead we just scan and as we scan record the counts, then what we find is basically we find that in each experimental run we actually observe a reasonably narrow resonance, and moreover there is some point here where basically the resonance vanishes completely. So this essentially corresponds to this instantaneous measurement of the nuclear field. And in this case, evidently we can do it faster than the nuclear evolution. So that's this kind of idea that if your environment is highly non-Markovian, you can actually make a rapid measurement of this environment. So, kind of in the spirit of quantum optics, one could then ask the question as well, can we somehow use this fast measurement to, for example, prepare the nuclear environment into desired configuration? This preparation can be done either in a kind of sense of post-selection. We just can only select the events where the field had a kind of right value, where the environment was in the right state. Or there are also some more advanced strategies like using the feedback. So I'll just talk about this post-selection idea. So essentially, the idea is actually very simple. So let's fix external magnetic field and monitor fluorescence. Let's just wait until the NV center becomes dark. If it becomes dark, namely that there are no photons which our detector detects, this means that our environment is prepared in a state such that the sum of the external applied field and the nuclear field precisely add up to zero. Right? That's the idea. Right? So we basically can wait until our environment is in exactly the right state. And then, for example, if you want to do some experiment, we can do it afterward. So this is how we verify this kind of preparation. So this is, once again, this is the average over all carbon-14 configuration. And then what we do, we fix magnetic field and just shine light on the center and basically look for colors. So if we don't do any kind of post-selection or any recording of the counts during this preparation step, we already see that even just the presence of the pumping field modifies our original kind of nuclear field distribution. In this case, what we see is some new peak start to emerge. So that's actually a result of optical pumping. So in this case, this optical pumping mechanism is a bit more complicated than in case of just one nitrogen, but nevertheless it's present. But then if we only keep the cases when the NV is dark, then what we see is that basically this kind of distribution is broad, feature is completely eliminated, and we just get an error peak. So once again, the way how these experiments are done is that you first prepare the NV center, and then you do a rapid scan, just to make a measurement of its line. And what you see is a line with narrows, and that corresponds precisely to this kind of post-selection, to selecting the events where the environment is in a kind of inner right state.
So let me make sure I've understood. You, at some fixed value of B, you see that things are dark. Then you scan B, and you see this deep dark resonance at the value that you formerly found that the thing was dark at.
That's precisely. If you do this scan, fast enough.
Yeah.
That's right. So that's kind of, okay, that's a simple, a little bit, kind of, it's a simple way how one can, do this kind of environment engineering. So that's one of the ways how one can control the environment by basically non-Markovian environment by making a measurement and really, kind of keeping track of it.
So what's
So
the
how
cause
long
of
do you, I'm sorry,
Yeah.
how long do you have to wait typically until you get your environment right where you want it in the experiments?
That's an excellent question, Pierre. That's a part which I'm actually kind of skipping. So in this case, this experiment was done with the kind of natural abundance carbon atoms. And so in this case, we measured this, the times of about a millisecond. Right? But in the kind of in this quantum money experiment, which I'm not going to talk about, so there we can, basically have spins which maintain their orientation for like seconds, and coherence also. Yeah.
What's the cause of the line width that remains?
That's a very good question. I have a slide which I wanted to skip. But actually, okay, so basically, initially, of course, it's a power problem, and then what we do is we reduce the power and look what the limit is. So basically, theoretically, eventually it's a lifetime of nuclear spin which should be limited. And what, as I remarked here, we measure kind of that the nuclear spins evolve not on a single time scale, they evolve in a multiple time scale. And actually, there is some interesting physics that may be related to Levy flights, which we are now exploring. But but a kind of millisecond, about a millisecond would be a right estimate, so which means that we should really observe liveness on the order of kilohertz. So in our case, we do not quite reach this limit, and the reason turns out to be kind of subtle. So it turns out that that there is a mixing between these two states plus and minus 1 due to local strain. And this mixing is very small, it's tens of the kilohertz range, so normally we don't see it. But when we lined up, when we eliminated all sorts of perturbation, that's a limit which we reach. So we actually, in the meantime, know how to control this strain. I just apply an electric field. So in principle, this can be kind of eliminated, but that's what the limit was, at least at the time. Yeah.
What's the strain you just mentioned?
So strain is a form. So because we are in a crystal, what happens is that in a crystal, there can be some defects, or basically there can be some strain is just essentially kind of corresponds to kind of shift of the atoms from their non-equilibrium position. So and basically the way how the NV center feels it is through the electric field. So effectively the strain creates some electric field at the position of the NV center. To the leading order, the spin state does not feel this electric field, but it turns out in a very high order it does feel it a little bit. And that's a strain effect.
Okay.
So the strain affects very weakly the spin states. It actually affects very strongly the optical states. And actually, if you want to know more about it, you should look at Alp's poster. So there is a poster here which talks about the effects of strain and stuff. All right, so let me just wrap up this part by just saying that I already mentioned. So actually, I'm still kind of studying this effect, and in fact, this kind of time scale is an interesting question. So it's not just a single exponential, but I think we really can look at some kind of interesting corrective nuclear dynamics, and maybe something like the Levy flights is not completely clear if it's really the analogy is 100%. So of course, eventually, if you want to make this useful, you really want to put in some kind of feedback which will essentially compensates this field. This nuclear field, right? By just measure it and we compensate it, and then we can really make use of this for applications. So one application could be the magnetometry or optical magnetometry, but perhaps sort of more interesting is the direction where we can use this effect to kind of engineer the environment. For example, introduce some kind of engineer many-body dynamics or dissipation, and this actually has some application. For example, for long-lived memory, where we can now store qubits in this nuclear spin and really keep them coherent for many seconds, you know, and then retrieve them and kind of read them out with really high fidelity. And then, of course, you eventually would like to control coupled NV centers. All right, so this is kind of nominally the end of my first lecture. And let me now just see what we go to. So basically, so I covered pretty much everything except for this quantum money, but there has been a lot of talk about money yesterday, so I think it's a good sufficient. So I wanted, what I plan to do is talk now a little bit about, you know, basically quantum optics, essentially coupling these nitrogen vacancy centers with the light fields, and this of course brings us to the physics of KTQD. So how should we do it, Pierre? So in principle, this is good time to. So I could probably do like 15 minutes.
Yeah, you should probably not do more than 15 minutes because you have to go catch a plane at some point, your next lecture, and you have to catch a plane as well.
So I mean, I could either stop here and we have discussion, or I could talk a little bit about.
Well, let's ask the students what they want. If you want 10, 15 minutes, or if you would rather discuss with Misha during the coffee break, it's up to you. So who wants 15 minutes? I want to see a show of hands. Okay, who would rather talk over coffee? Nobody wants to talk. Well, so people who don't vote don't have any complaint that they can make.
All right, so let me talk.
So let's go for 10, 15 minutes.
Okay, so the goal of this 15 minutes will be to cover this last thing that you need to know. Right, and then go free. So basically, these things which I discussed so far allow us, in principle and in practice, to really create some very good memory and kind of registers which are composed from few quantum bits. But if you really would like to kind of build a full-scale quantum information system, you need some techniques for long-range coupling. You need techniques to basically to realize these quantum wires, to move the information around. And the potential solution to this was identified early on, and the solution was to basically use photons as an efficient quantum interface. So basically the idea, and this kind of very important paper in the field of quantum information, was that if you have the situation where you can store qubits, for example, in some spin states of atoms or recenters or something, and put them in a cavity, if you can make these atoms emit the photons and absorb them basically on demand. Then what you could do, you could basically copy these qubits, map these qubits into this database, and then let them propagate to another cavity, then absorb them, thereby establishing this kind of quantum unit. So this is by now a broad effort in the ML community. There is many experiments now with single neutral atoms, ions, atomic ensembles, and solid state emitters. But what's perhaps most exciting, in the last 5 or so years, a remarkable set of new interconnects have been developed. And these interconnects span optical domain, including starting from just bulk fabrication cavities to nanophotonic, nanoplasmonic cavities, to microwave, and all the way to mechanical domain. So this is now a really exciting field where this kind of basic concepts which originates in quantum optics and MO really is applied to many different systems. So there is actually a set of some really unique opportunities which if you can implement these techniques, will be enabled. So in particular, you can control spatially and spectrally the spontaneous emission of the emitters. You can basically tune the frequency of the emission. You can change the direction of the emission. As I already mentioned, you can do quantum information transfer. This kind of the most basic idea is this kind of single photon passing catch. You create a single photon which has some quantum information coded in it, and then you store it in a different ensemble. So this directly allows you to implement things like long-range quantum gates between distant qubits, but also another important thing is basically to do nonlinear optics at a single photon level. This is like a holy grail of the nonlinear optics for many decades. So, okay, but it turns out implementing these ideas is quite challenging. So let me talk a little bit first at the intuitive level why these things are challenging, and then I will do another blackboard part. So basically the question which I'd like to ask you is, so suppose I have one photon which is focused, say in a Gaussian beam to the diameter d, and I have some atoms in a gas. So what's going to be the probability, the maximal probability that a single photon will interact with a single atom? Does anyone know the answer? So what's the maximal probability that a single photon will actually hit the single atom? Any thoughts? The things which are given is the localization of the photon, the transverse localization of the photon, and the wavelength of the photon. The maximal probability allowed by nature is going to be what? So if you have a, what's it called? Optical theorem and scattering theory. So what's the maximal cross section? Let's specify. What's the maximal interaction cross section between the photon of the wavelength lambda and any subwavelength object? So if the object is just a dielectric sphere of radius a, then the cross-section will be a squared or something like this, right? Right? So, but what if the object has resonance? What's going to be the maximal cross-section at resonance allowed by nature? What? What's again?
He said 4 pi a squared.
That's so. So this is okay. Let's do this. So you have a ball of the size a, and then there is something coming into it. Indeed, the cross section will be on the order of a squared. Right? But what if now, and so suppose that a is much smaller than lambda. So, but what if this object has a resonance? Can the cross section be larger at resonance? Exactly. So it can be larger, but it cannot exceed lambda squared. Right at resonance, the absorption cross section will always be maximized at the lambda squared. Cannot be bigger, right? Let's connect it to basically wave nature things, right? All right, then we can answer my question in a very simple online formula. The maximal interaction between probability of interaction between single photon and single atom will be given by lambda squared over it, right? So it's like, think about the photon propagation as a flow of the liquid in a pipe. And there are these kind of atoms which are like little plugs, right? So basically, that will be the probability that you hit the obstacle. So interestingly, if you ask a question, now a reverse question, what if the atom now is excited? What's the probability that the photon will be captured in this mode? It actually will be of the same order. Why is that? It's because the processes of absorption and emission are related, right? They are kind of reciprocal. Right? So in fact, you can think about this absorption process as basically as an interference of the incoming wave and the wave which is emitted by the atom. Right? It's kind of a destructive interference which causes the absorption. Right? So for this reason, basically the spontaneous emission, the fraction of spontaneous emission that you will capture in a single mode will also have this lambda squared over Q. So in practice, usually it's hard to focus light close to the wavelength, and for this reason, both of these quantities are quite small. The essence of cavity QED is essentially to put a pair of mirrors around the atom, and what these mirrors will do is they will essentially enhance its probability of interaction by essentially making the photons circulate between these mirrors for many, many times. Right? The number of the times that the photons circulate, the number of bounds that it will make in the cavity before escaping is essentially given by the finesse of the cavity. That's one of the characteristics of the cavity. So, basically the same thing will happen with spontaneous emission. The spontaneous emission, the given mode, will also be enhanced by a number of bounces. What you see is that eventually, when this probability is on the order of unity, then this emission into this mode will actually exceed the emission into a free space, and that's, of course, the essence of something which is called Purcell effect. By putting the atom in the cavity, you can accelerate the spontaneous emission. So that's the idea, essentially, of cavity QED, to make this thing big. So, okay, so I promised you 5 minutes of blackboard lecture, and this will be my concluding. So, what I told you just now is all perfectly correct, and this gives us a right intuition about what's going to happen. To make these considerations kind of more quantitative, it sometimes is helpful to consider the most basic model of the atom field interaction, and this is what is sometimes called cavity QED. It's basically a situation when one atom interacts with one mode of radiation field. So basically the picture here is that you have some sort of cavity, from a raw cavity or maybe a photonic cavity, and you have an atom in this cavity, and basically the atom can basically, if the atom is excited, it can decay into this cavity. Right? So what determines this rate of decay? How can one calculate it for the first place? So one, of course, has to start with some kind of Hamiltonian. So we remember that in a kind of semi-classical theory, we had the classical field, for example, if this is G E, the classical field will be sort of deriving, transition from G to E, but now we have to really quantize the field. So basically what we need to do is replace this classical radio frequency by for example, the equation operator corresponding to the atom making a transition from E to G, and one photon is created. But then, of course, there should be a coupling constant here, G in front of it. And this is this thing which is the rule number, what's it called? Fact number 4. Right. So this thing is basically a radio frequency of one photon, or as I was mentioning before, as sometimes called a little bit misleading way, the vacuum radio frequency. So what is this G and how to calculate it? Who knows how to calculate G?
Quantize the electromagnetic field.
Who knows how to calculate G before my time is up?
It's proportional to 1/square of the volume.
Why?
So you quantize the electromagnetic field in a confined boundary condition.
So here is kind of the last thing I'm going to do for you. How to derive G and not run with it. So it can be derived from the following consideration. You are right. It depends on volume. Why does it depend on volume? So let's consider a situation where I have one photon in a cavity, and of course I know that the energy should be h bar omega. So let's calculate the electric field which corresponds to this one photon in the cavity. So this electric field can be calculated classically as basically energy density of the electric field multiplied by V. V is a mole volume of the cavity. So from this expression we can immediately find out what this quantity E0, which is basically an electric field per photon, is. Right? So this E0 will be square root of h bar omega over 0V, and this immediately results in a radio frequency, which is basically the dipole moment of the optical transition times 0 divided by h bar, and this is square root of this. Right? So that's the thing that we need to know and understand deeply. Right? Once you know this, you can do a lot of interesting things. So what determines the dynamics in this KDQD is the ratio between this G, this the rate at which basically the photon and atom excitation is exchanged coherently versus the decoherence parameters. So in particular, if you create one photon in a cavity, it will decay with rate kappa. At the same time, the atom can also emit in other non-confined modes with the rate gamma. So there are basically two important regimes that you need to know about KTQD. And one of them is referred to as strong coupling. And this is a regime where this G is much larger than both kappa and gamma. Right? So this is a situation where atom and photon can exchange interaction many times, can exchange excitation many times before the photon leaks out. But there is one second regime which is also very important, and that's what I would call Purcell regime. So in this regime, G squared can be smaller than kappa, but nevertheless, once one can reach this Purcell regime, the regime basically where when the photon decays, it mostly decays in a cavity mode. Right? So basically the atom, in this kind of incoherent way, the atom and photon cannot exchange the excitation forever. But the atom can still decay among two channels. It can first decay in the free space, or alternatively, it can emit the photon in a cavity, and then from the cavity, the photon can decay. So basically, this Purcell regime, the atom decays through cavity predominantly. So So even though this looks like it's a kind of incoherent process, it turns out that in this Purcell regime, once you can make the atom decay in a given chemistry mode, you can basically rule the world. You can do anything. The condition for that to happen can be calculated easily by using rule number 3. Right? So, and the idea here is the following. So basically, if we start with the atom in the excited state and we have this atom field in direction G, right? Then, so you start with atom in excited state, the photon in cavity. You go in the state where the atom in the ground state and there is one photon in cavity. But then from this state, basically, the photon can decay outside of the cavity, right? So once again, what we have is we have this coherent coupling G and the decay. So what's the rate of this photon decay through the cavity mode? What's the rate?
G
So it's G over kappa. So this is the cavity decay. And this has to be compared with the direct atom decay. So this is atom decay through cavity. So what you see is that this Purcell condition is fulfilled when G basically over kappa and gamma is much larger than 1. Note interestingly that the dipole moment enters both G squared and gamma in exactly the same way. So if you kind of do some algebra, what you realize is that this thing is nothing but a lambda squared over D squared times thickness of the cavity. Precisely the same thing which we absorb. All right. So
areas with the second regime be useful at the one hand.
So if you can reach the second regime, if the Purcell factor is large, then you can implement any imaginable quantum information protocol. So for example, you can let atoms exchange photons with fidelity near you. Okay, so 2 last remarks. First of all, what does this imply in terms of realization of the systems? So you would like to have a cavity which will have high finesse, but also you want this cavity to be small. So by making D as close to wavelength as possible, or squeezing the photons below the wavelength, even the finesse of the cavity is modest, you can achieve a huge Purcell factor. And this is what the rest of my slides were supposed to tell. That's the message number 1. The message number 2, I hope, for this discussion, you got a little bit of the feeling of how this kind of basic concepts of atomic physics play out in very different settings, in the settings which often will be beyond atomic physics itself. And the only thing which I want to add to it is that if you internalize this concept, if you understand them deeply and apply them creatively, you can do a lot of wonderful things. Thank you very much.
Thank you very, very much, Mikhail. We don't have a whole lot of time for questions because as I said, some people want to catch flights, so we want to remain on schedule. But if there is a couple of urgent questions, we can deal with them, and otherwise we'll do it during the coffee break. So I want urgent questions. I don't want to discourage questions, but I want the 2 best questions of the day. At some point I used to offer money for questions, but I've not done it in a while because the stock market has
There was a lot of, I asked a lot of questions.
Well, I have no shame, so I'll answer. You talked about this strain-induced shift. Why does